Guys, so we are on Unit 4, Part 4. This is the end of Unit 4. This is our second set of notes on vectors. Okay, so we had Part 1 and 2 over law of sines and cosines, and then yesterday we did Part 3 over intro to vectors. Now we're going to be looking at vectors in the coordinate plane here. We're actually going to take a more algebraic approach to vectors, as opposed to yesterday we were doing a more geometric approach. Okay, so you can see here in this first picture on the left, we've got vector OP. It's in standard position starting at the origin. Okay, when you have a vector in standard position, it can be described by the coordinates of the terminal point here, point P, which is X, Y. Okay, that notation with that point is called component form. Okay, and it's represented, it looks like this, where these are not, the ordered pair is with a parenthesis. Okay, these are kind of like a pointed parenthesis bracket. Okay, and we're going to draw some by hand. You'll see how I draw them as well. Okay, now because the X is the horizontal component or horizontal distance, and Y is the vertical component or vertical distance from initial to terminal point. Okay, now in this second picture, you can see here's that vector OP in the middle. They're saying it's over 3 units and up 2 units. Vectors W, T, and V are all equivalent vectors. They're all the same size. They're all the same direction, but they're not in standard position. But we can still represent them in that same component form of 3, 2, because they're equivalent. They're the same size and direction. Now, if it's not in standard form, it's not going to just come from the terminal point. To get those components, we use this little expression here to calculate that horizontal and vertical component. So you can see here, we find the difference in the horizontal. So x2 minus x1, that's the horizontal distance. And then we do the same thing for the vertical change, y2 minus y1. And that gives us our component form. Okay, and again, I know I said this, I'm gonna label it on here. We call this the x2 minus x1. The value that goes here is our horizontal component. Okay, and then the change in y here we call our vertical component. Does this make sense so far? So we can use this component form notation to represent our vector. And we can tell that direction, like 3, 2, that means right 3 up 2. So you can tell the direction that it's pointing. Okay, and you determine from those numbers too, you can determine the magnitude. Okay, we're going to get more into that in a second. All right, I'm given the initial and terminal points of vector AB, and I want to write it in component form. So the first thing I'm going to do is label my points, x1, y1, x2, y2. Okay, and I'm going to write out my expression. It's x2 minus x1 and y2 minus y1. All right, so I'm going to color code what I'm plugging in. So I'm going to do x2 is 3, x1 is -4, y2 is -5, and y1 is 2. So my component form, what happens when I subtract a negative? Yeah, that becomes plus. So my horizontal component is 7. And my vertical component is -7. So the direction of this vector from its initial point to its terminal point, you would go right 7, down 7. Does that make sense? All right, now, I said we would get into finding the magnitude from that in just a minute, and that's what example 2 asks us to do. So I'm actually going to show you 2 different ways. Because we already have this in component form, you can kind of imagine the triangle. So you said you know it's going right 7, down 7. So here's what the vector looks like. Y'all agree? Okay, that forms a right triangle, doesn't it? So could I do Pythagorean theorem? So I could do 7 squared plus -7 squared equals, well, we can say c squared or whatever you want to represent the vector. So that's 49 and 49, which is 98. And we take the square root.
Can I retake quiz like before the break?
Right now?
Yeah.
Are you in your base? Sure.
I just did that somewhere.
All right, so we're doing a factor tree here to simplify because a 98 is not a perfect square. So you can see the factors I used were 49 and 2. 2 is prime, so that branch stops, and then I kept going here to 7 and 7, and those are prime. So that breaks down. 7 gets to come out. Square root of 2 stays in. So I get 7 square root of 2 as the magnitude, the length of that. It does. So good observation. So if you make the connection here that this is an isosceles right triangle, because these are both 7, and you remember your special right triangle ratios, that this is x, and x square root of 2. If you know those ratios, because I'm not going to give you those ratios, that's something that you're supposed to know. So if you have those memorized and you know when it's isosceles, this is just x squared root of 2, then you know right away it's 7 square root of 2. And you don't have to go through that work. Okay. Now, the other option, if you don't have it in component form already, let's say we hadn't done this already, which, I mean, this is the exact same initial and terminal points, the same vector we're using here. Okay. You could use this, which is distance formula. Okay, so you could plug into distance formula, and that would be 3 minus -4 squared plus -5 minus 2 squared. And in the parentheses there, that's what we already did in the previous example to get 7 and -7. So we jump to 7 squared and -7 squared under the radical. And now we're in the same boat we were over here, right? That's 49 and 49 adds to 98. So we're at the square root of 98, which we already reduced over there to 7 root 2. So you get the same answer using distance formula versus Pythagorean theorem, or if it's a special right triangle, you could have used that as a shortcut. Yep. So if you don't have it in component form, distance formula might be best. Okay. Or you can put it in component form and then do Pythagorean theorem. However you want to think of it. Or some of y'all are going to get to the point where you just know, I'm going to put it in component form, and then you're going to jump straight to this step here. You're going to say, okay, so it's 7 and -7. That means I'm squaring and adding them together and taking the square root, which is what you did over here. You squared them, you added them together, you took the square root. You just did it step by step in Pythagorean theorem, right? Okay, so when you are asked for the magnitude, that's the process, that's what you're doing. Okay, and you can use any of those methods. This symbolizes these bars will look like they're like really close to, sometimes it looks like one, but they could be like double bars like that around your vector. That means magnitude. That means they want the magnitude. Okay. They want the length of the vector.
I thought it was absolute value.
That looks like absolute value symbols. Yes, that's why I'm highlighting it and explaining in for vectors. When you see that symbolism, they're asking for the magnitude. Okay. And it is absolute value also, like if you think of it that way, because it always should come out positive because we're talking about the length of the vector.
Yeah.
So you know, maybe maybe thinking of, oh, that's absolute value. Oh, that's the length. It's positive. It's a length. You can think of it that way. All right. So let's try this one. New problem. What we were just going over. Y'all give it a shot. I'm going to freeze the screen. If you're watching this on video, you can pause and try it and then come back to check your answer. Okay, so you're given the initial and terminal point. You want to find the magnitude. My hint is to put it in component form first. Turkey. Are you retaking it? Stuffing. All right, y'all think you've got it? What'd y'all get? 8 square root of 2 is correct. And this is another one that it turns out being a special right triangle. So there's actually 3 ways you could figure out the magnitude once you have it in component form. So the component form would be 8, 8. Okay. You can jump straight to this portion of the distance formula. You could draw it out and do Pythagorean theorem, or draw it out and realize, oh, that's isosceles. So that would be 8 root 2. Whichever method you prefer. Okay, if you're doing the distance formula or Pythagorean theorem and you get to this point where you're taking square root of 128, you have to do your factor tree and simplify that. You feel okay about those? Finding the magnitude, putting in component form. All right. So what we're going to look at next is some vector operations. So adding and subtracting vectors and multiplying them by scalars. Okay, so remember, a scalar is just a number that does not have direction. It's just an individual value. Okay, so if you're multiplying a vector by a scalar, so they're telling us A and B are vectors. So K is a scalar. So a scalar times a vector, that scalar gets multiplied by both components. You do K times the horizontal component and K times the vertical component. You can kind of think of it as distributing the scalar to both components. Okay, now addition and subtraction, you subtract or add the like components. For instance, in vector A sub 1 is the horizontal component. In vector B sub 1 is the horizontal component. So if you're adding vectors A and B, you add their horizontal components. If you're subtracting the vectors, you subtract the horizontal component. Same goes for the vertical components. You just add them or subtract them. Okay, so we're going to try that here in example 4. So I'm going to write out the vector W plus, and then I'm going to write out the vector Y. All right, so I identify the horizontal components. I identify the vertical components, and that's what I add. You can jump straight to your answer probably. For the sake of our notes, I'm going to show that I'm adding -4 and 2, and then I'm adding 1 and 5. So this middle step really doesn't have to be written every time. You're going to get the hang of this and be able to go straight from there to your answer. So that is the resultant vector in component form. Pretty straightforward, right?
Yeah.
Okay. Now B is a little tougher. It's subtraction and it has a scalar being multiplied. Oh, you know what? While I'm thinking of it, I do want to point something out. I thought of this while y'all were working on this last one. Because somebody had asked in a previous class, does it matter on point A and point B, which one is x1, y1, which one is x2, y2? What do y'all think? Do y'all think it matters which one?
Yeah.
Why does it matter?
I know it could have negative in it.
In this particular problem, they're just asking for the magnitude, so it didn't matter because the magnitude doesn't matter what direction it's in, does it? It's the length. So the length from the initial spot to the terminal spot versus the terminal spot to the initial spot, it doesn't matter which direction you measure, the length doesn't change. But it does matter which is the initial and terminal point if you're having to find the direction. So just keep that in mind. It does matter. Initial point should be x1, y1. Terminal point should be x2, y2. Okay, I just wanted to point that out before I forgot. All right, now here, I'm going to list out vector z. And we are subtracting 2 times vector y. So it says up here for scalar multiplication that both components get multiplied by the k. So I'm going to do that first. I'm going to take 2 times 2 and 2 times 5. So this becomes 410. So you're doubling that vector. It's twice as long now, right? So that is what I am subtracting from vector z. So again, I'm going to identify the vertical components and the horizontal components that need to be subtracted. And the order does matter because it's z minus 2y. So it should be the -3 minus 4 and 0 minus 10. So -7, -10. Is that different? When we do the delta math practice tomorrow, there's going to be some practice with adding and subtracting vectors, and that you'll get to, it'll guide you through what that looks like graphically, subtracting the vectors as well. It might help you understand that process a little better to see, have that visual. Okay. All right. Now, a vector that has a magnitude of 1 is called a unit vector. Similar to how we called the unit circle because it had a radius of 1, right? And it was centered at the origin. So a unit vector is 1 unit long. Now, it is sometimes useful to take some vector and rewrite it as a scalar multiplied by a unit vector, okay, going in the same direction as whatever that original vector was. To figure that out, to do that, to get the unit vector that would go in the same direction as some other given vector, you would take the given vector divided by its magnitude. Okay, that's how you would do this. Okay, so we're going to try that in example 5. So I want to find the magnitude, or excuse me, I want to find a unit vector that goes in the same direction as vector v. So vector v divided by the magnitude of vector v. I need the magnitude to go here. We said once it's in component form, to get the magnitude, it's going to be the square root of the sum of those components squared, right? Do y'all agree with finding the magnitude that way? Does that make sense? So I put the vector over the magnitude of the vector. Okay, so I'm going to go ahead and simplify that a little bit. So that's 4 and 9, that's 13. So square root of 13 is the magnitude. Okay, so that's what we found for magnitude. Now you can see here, it says, if it makes more sense to you, you can write it this way. You can pull that denominator out as a scalar being multiplied, be 1 over that magnitude. So what I'm about to write is not required, but it may help as a visual for some of you to see. If I pull out that square root of 13 denominator, it's 1 over square root of 13, right? There'd be an understood 1 here times the vector. You don't have to write it that way if you understand it this way, but you have to know that scalar division would work the same as scalar multiplication. So that scalar would get multiplied by both components. Or if you don't write that step, think of it here. This scalar would get divided, right, by both components. So that becomes -2 over root 13 and 3 over root 13. Okay, so this is the unit vector that goes in the same direction as this vector v. We don't typically leave answers with radicals in the denominator, so I'm going to rationalize it. Just one little quick extra step. Y'all know how to rationalize, right? So what would this become? Mm-hmm. Over 13.
Oh,
Good.
okay.
And what would this one become? Good. So there's that unit vector that goes in the same direction as this vector v. But this one is 1 unit long. Feel okay about that?
I think so.
Okay. I'm going to do just a quick little color code here so you can compare it to this. So what we did here, that was this. And then we rewrote it. If that is helpful, that's that format. So those match up to that. Okay. All right. So next up, we're going to talk about what's called a linear combination. Okay, so it's a different form of writing your vector instead of component form. So to write it as a linear combination, you do need to know the component form. So either it may be given to you in component form, or it may be given to you as an initial point and terminal point, and you put it in component form. And then from there, you can put it as a linear combination. So what this means is, we talked about a unit vector is 1 unit long. And the unit vector that goes along the x-axis and the y-axis are special. They are called the standard unit vectors. Okay, and we use I and J to represent those. So I is the horizontal standard unit vector, and J is the vertical standard unit vector. Okay, any vector that you have, so in this picture here, vector V, okay, which in component form we're calling AB, you could rewrite this as a linear combination of I and J. So you would just count out how many I's do I have to go over, because they're 1 unit each, right? So whatever your A is, you would multiply it by I. And that means it's the horizontal. And whatever your B is, you would multiply that by your J. And if I add those together, like if I moved that tip to tail, isn't this the resultant vector?
Yes.
So you add AI plus BJ, and that gives you this vector. And when you write it in that format like that, it's called the linear combination. The linear combination of vectors I and J. Okay? So that kind of explains where this comes from, because you're adding the horizontal and the vertical components to get that resultant vector. You're doing it in terms of those standard unit vectors. So let's apply that. We have vector DE. They gave us the initial and the terminal point, and they want us to write it as a linear combination of vectors I and J. So the first thing is we need to put it in component form. Okay, so if you need to label still, go ahead and label. So that's X1, X2, Y1, and Y2. So that would be 4 minus -2 and 5 minus 3. So the component form is 6, 2. Everybody okay with that? Component form? So now from component form, so this is like what we said on that last screen. That's your A and your B, right? So if linear combination is AI plus BJ, this would just be 6I plus 2J. They're saying you could take vector I, which is the standard unit vector along the y-axis or x-axis, multiply it by 6. You could take vector J, multiply it by 2, add those together, and that would give you that vector DE. Okay? That is the linear combination. All right. Now, what if you're not given the terminal point and the initial point? Instead, you're just given the magnitude and the direction. We can still find component form and linear combinations with that information. And I'm going to explain quickly how. So if we think about our vector V here, okay, this would be the X movement and the Y movement, right? Or you could call it A and B. Doesn't matter. X, Y, A, they're calling it AB here, so I'll call it AB. Okay. Right triangle trig tells us that from theta, this is opposite, this is adjacent, and this is hypotenuse, right? Okay, so in component form, this is A and this is B, and the vector here, the magnitude of vector V is the hypotenuse. So I could say cosine of theta is the adjacent over the hypotenuse, so that would be A over the magnitude of V. And I could say that sine of theta, which is O over H, would be B over the magnitude of V. If I wanted to solve for A and B, I would just need to multiply that magnitude of V over, right? Move the denominator to the other side by multiplying. Do y'all agree with that? So what that is telling us is this is the horizontal component. You can replace A with that in component form. This is the vertical component. You can replace B with that in the component form. Okay, and remember, this is the magnitude of V, the magnitude of the vector, and this is the direction angle. So if you know the magnitude and direction, you don't need to know the ordered pairs. You can still put it in component form. So I'm going to label these real fast. This is the horizontal component. This is the vertical component. Okay, so we're going to try and apply this. Instead of being given the ordered pairs of the initial and terminal points, they're told the magnitude of the vector is 10 and the direction angle is 120. Okay, we want to put it in component form. Well, we know that the magnitude times cosine of theta is the horizontal, and the magnitude times sine of theta is the vertical. So I can plug in the angle, the direction angle there, and I can plug in the magnitude here. That would be 10 times cosine of 120, and this would be 10 times sine of 120. Now you do have a calculator for this test. You'll get to use a calculator, but 120 is from your unit circle. You should know that angle 120. Who knows it? Who knows the ordered pair at 120 degrees on the unit circle? It's a 60-degree reference angle, right? What's the ordered pair at 60? No, not the radian measure, the ordered pair, the XY value.
Okay, so it goes. So it should be.
Which one of these should be negative since we're in quadrant 2? We're going from the origin, we go left and up. So the X needs to be negative, the Y is positive. So at a 60-degree reference angle, X is 1/2, Y is √3/2, but since this is in quadrant 2, that one needs to be negative. Which is which as far as sine and cosine?
Cosine's the first one.
Yeah, cosine is the X, sine is the Y. So cosine of 120 is negative 1/2 times the 10. Sine of 120 is the √3/2. So that would be -5. That would be 5√3. Now, if you used a calculator, you're in degree mode and you do this in the calculator, you'll get the -5 just fine, but you're going to get a decimal here. And if this is a multiple choice on a quiz or a test, it's not going to be as a decimal, it's going to be as that radical. So do y'all know you just type in your answer choices, they're radicals, type them in and see what are they as decimals and match it to the decimal that you got. Okay, you can kind of work backward from your answer choices if that's what you're doing. If you absolutely cannot remember your unit circle values, you have to use the calculator to get a decimal. Get all of your answer choices as decimals and compare. Okay? All right. Let's try finding an angle. So that was finding, that was given the magnitude and the direction, find the component form. Now here we're given either the linear combination or the component form, and we want to work backward to find the direction angle. So we know from all semester of trig, we know that tangent is the vertical divided by the horizontal, right? In a triangle, let's go back to where we have a triangle pictured. If I want to find tangent of this angle, it's O over A, right? It's the horizontal component divided by the, I said that backward. It's the vertical component divided by the horizontal, right? It's B divided by A. So that's what they're telling us here in this highlighted section. It's B over A. It's the magnitude times sine of theta over the magnitude times cosine of theta. Okay? So we're going to use that knowledge. We're going to apply that to vectors, what we're doing. If this is the linear combination, remember that's A, I, plus B, J. Aren't they telling us A is 3?
Yeah.
And B is 7? That's what they're telling us. The component form would be 3, 7. Y'all agree with that? Okay, so I worked backward from linear pair to component, and most of you are going to be able just to write that down directly. You don't have to write that in between. I'm just for the sake of our notes. Okay, so here's the component form. That's the A, that's the B. So to get the direction angle, it's B divided by A. So 7 divided by 3. How do I solve for theta? How do I get rid of tangent? Good. Inverse. I make sure my calculator's in degree mode and I plug that in and I get approximately 66.8 degrees. B is a little easier because it's already in component form, right? That's the A, that's the B. So if I want to know the direction angle, I'm doing -5 over 4. I have to do inverse tangent. Now, when you plug that into the calculator, those of you following along may notice already, if you're not, this comes out negative. The calculator tells you -51.3. We're not going to give negative angle answers, but you should be able to tell me -51.3 as a positive angle. How could I figure out what it is in the positive direction? Yeah, 360 minus 51.3. Remember, this goes back to coterminal angles. We learned those for a reason. So the angle, the direction angle is actually 308.7 degrees. So far, so good? Okay, almost done. Last example. We're going to apply. Application here. The quarterback running forward 5 meters per second throws a football with a velocity of 25 meters per second and an angle of 40 degrees with the horizontal. What is the resultant speed and direction of the pass? Okay, so they give you a little graphic there to help you understand what that looks like. Okay, so we have the direction angle. and we have the magnitude of his throw, and we have the magnitude of the vector representing him running, right? What would be the direction of him running? Yeah, what would that be as an angle, degree?
0.
0 degrees, good. Okay, so I'm gonna put that on my picture. So this vector, the magnitude is 5, the direction angle is 0. And this vector, the magnitude is 25, the direction angle is 40. Okay, so that's what I'm gonna first put both vectors in component form. I'm gonna try and write out like step-by-step instructions here. So put vectors in component form. Okay. So I'm going to do the magnitude of the vector times cosine of theta, the magnitude of the vector times sine of theta. This is how I do that when I know the magnitude and the direction. Okay, so for the first vector, the quarterback running, that's 5 times cosine of 0 and 5 times sine of 0. And the second vector, for the throw, it's 25 cosine of 40, 25, oops, I started to write cosine again. It's supposed to be sine. Get my little delete here. Sine of 40. Okay, so I use my calculator and I calculate both of these. This one at 0 degrees, hopefully you don't need a calculator. Hopefully you know sine and cosine at 0 degrees. Cosine is 1, so this is 5. Sine is 0 at 0, so this is 0. Okay, so that's him running. That's the quarterback. And then this one, you do need the calculator for. It comes out to approximately 19.15, 16.07. Now, they're wanting the resultant speed and direction, right? They want us to add the vectors. They want the resultant vector. Doesn't that mean add the vectors? Okay, so that's step 2. Add the vectors to get the resultant. All right, so I would be adding the horizontal component, that's the 5 and the 19.15. And I'd be adding the vertical, which is the 0 and the 16.07. So we get 24.15, and that's still 16.07. Everybody okay with that? So that's the resultant vector as a component form, right? Y'all agree?
Yeah.
Okay, so now I'm going to find the magnitude. To find magnitude from component form, remember I square both components and add them together and take the square root. You'll agree with that? Okay, so when I do that, the magnitude comes out to be approximately 29.01, and they did give us a unit. This is meters per second. Okay, so that's the magnitude or the speed of the ball when you combine his running speed and his throwing speed. Okay, so the ball's actually traveling a little faster. All right, now we need we have the magnitude, we need the direction. Okay. So for the direction angle, we said from component form, we can use Tangent of theta is b over a. We end up doing inverse tangent of that ratio. And that comes out to approximately 33.6 degrees. So now I have the magnitude and the direction. So I'm ready to give my solution for the resultant vector. I'm going to give it in the context of this problem. I'm going to say the ball is going 29.01 meters per second at a 33.6 degree angle with the horizontal. Notice I'm specifying my direction angle is from the horizontal. It's not a true bearing, it's not a quadrant bearing, it's measured from the horizontal. Okay. You feel okay about that? All right, so we ended both days with kind of a word problem, an application problem. Those take a little longer because there's multiple steps to them. Okay, and you got to think through what you're looking for. It kind of combines everything we learned. So tomorrow in class, we'll be doing a practice with vectors on Delta Math. I'm almost done making it, so I might go ahead and activate it if anybody wants to start tonight. I'll send a remind once it's active, or you can just check later tonight and see if it's there.
Until we got to here. And then stuff started getting wacky.